So next we'll discuss the volume energy term, which is the first term. So if a nucleus has large number of nucleons, then the size of the nucleus will be bigger, then the volume of the nucleus will be bigger. So in this case it will be more difficult to remove a nucleon from the nucleus. Okay. So if it is more difficult to remove a nucleon, it means that the nucleus is more stable and the nucleus has a greater binding energy. So we can say that if the volume of a nucleus is greater, then the binding energy of the nucleus is also be greater. Or if the volume of the nucleus is greater, it means that it has a more number of nucleons and it has a greater binding energy. So as we are deriving this term as per the liquid drop model, and in liquid drop model we assume the nucleus to be spherical. So for a spherical nucleus of radius r and mass number a, this volume energy term will be proportional to the volume of the nucleus, and or BV equals to RQ. Why? Because the volume, we know it is 4/3 pi RQ. So as we are using the proportionality sign, we are ignoring this constant factors, or BV equals to A. Okay, BV proportional to A. Why A? Because we know R is, the radius is R0 into A to the power 1/3. A is the mass number or total number of nucleons. Okay, where R0 is nucleus parameter. Or BV equals to plus AV into A. Where AV has this value, it is called volume energy coefficient, and it has a value of 15.81 mega electron volt. So this term is positive. The positive terms, it means that it indicates that, because later we will find that the other terms may be negative. This positive term indicates that it contributes to, the volume energy term contributes to increase binding energy, not decrease. So as the size of the nucleus is bigger, volume is bigger, then the binding energy will also be greater. So this volume energy term contributes positively to increase the binding energy. The second term is called the surface energy term. Okay, the surface energy term arises because we have said in the property of liquid drop model, of course the nucleus acts like the surface of the nucleus acts like a surface of a liquid drop. That is, there will be surface tension kind of forces, or the effect of surface tension acting on the surface of the nucleus. Okay, so why this happens? It happens because the nucleons on the surface of the nucleus are not surrounded completely by the other nucleons. So here you can say that, suppose if we have a nucleus like this, where we have these nucleons. Okay, so if you look at the nucleons which are at the surface here, they are not surrounded by nucleons, by other nucleons completely, unlike these nucleons which are inside. Inside these nucleons are completely surrounded, but these nucleons on the surface are not surrounded completely. As a result, what happens is surface tension kind of effect. Surface tension kind of effects acts on the surface of the nucleus. Okay, so because this nucleus, as these inside nucleons are completely surrounded by other nucleons, it is very difficult to remove any interior nucleon. But this surface nucleons, as they are not completely they are not surrounded from this side, it will be easier for us to remove one nucleon. So you can say that for this nucleons, kind of binding energy is greater compared to this nucleons. To remove one interior nucleon, we have to supply greater energy compared to those nucleons on the surface. We have to supply less energy to remove any nucleon for the surface. So because of this kind of phenomenon, what happens? The binding energy decreases. Okay, so because of this, they are this surface nucleons are loosely bound. They are loosely bound to the nucleus compared to the interior nucleus. Okay, so this effect decreases total binding energy and make the nucleus less stable. Okay, so this surface energy term Bs is therefore proportional to the surface area of the spherical nucleus, because if the surface area is greater, then there will be more nucleons on the surface. Okay, so as there will be more nucleons on the surface, for each nucleon we have to, each of them will reduce the binding energies to some extent. Okay, as a result, this binding energy term is the surface energy term is proportional to the surface area of the spherical nucleus. If the surface area greater, there will be greater number of nucleons on the surface, and they will decrease the binding energy even more. So Bs is proportional to R square. Why? Because the surface area, we know it is 4 pi R square. Okay, and R we know is proportional to a to the power 1 by 3. So R square will be a to the power 2 by 3. So finally we have this surface energy term Bs equals to minus As a to the power 2 by 3. The negative sign here indicates that the surface energy term reduces the total binding energy or the stability of the nucleus. Okay, so As here is called the surface energy coefficient, and it has a value of 18.34 mega electron volt.